from Gnode Labs, and I'd like to talk about our custom kernel approach. And the talk is structured the following way. In the first chapter, I'd like to talk about what motivated us to create our own kernel. In the second chapter, I give a little overview about general qualities of this kernel and how it works in general. And in chapter 3, 4, and 5, I will go into detail about some features of the kernel. And yeah, let's start with the motivation. One big advantage of Gnode is that you can run it off various kernels like Nova, like the L4 kernels, like SL4 or Linux, and so on. And that gives you a great flexibility in development and application of Gnode. So you can, for instance, some kernels have a cool debugger built in, and some kernels are specialized on security, like the SEL4 kernel. And so you can choose in the application and in the user applications. It doesn't matter which kernel you use for the basic features. And the second big advantage of supporting many kernels is that you have a lot of different ways of testing the system on top of it. So you have different timing, you have different scheduling, you have, in general, a different behavior at the base. And so you can get much harder testing for your system on top. Yeah. So when you look at this combination, Gnode and the kernel, it's normally the way that you have a microkernel that is developed on its own and that aims for a comprehensive security concept. So it likes to be self-contained and mistrusts all that is on top of it. Of course, this brings a little bit of problems with it because you then have the core, Gnode's core component that has to bring this paranoid kernel perspective in line with the Gnode API on top of it. And the misery here is that the core component of Gnode must be trusted anyway by all components on top. So you don't get, you don't have much advantage from this extra effort you spend in. So, of course, there are some drawbacks that come from this aspect. First, you have to shape some concepts the way you like it to be. For example, on some kernels for asynchronous communication, you have semaphores, for instance, and these semaphores must be bent in shape to support the asynchronous communication API that we use on Gnode. So the signals in this instance. So the other thing is that often work is done redundantly. So the memory management, for example, must be done redundantly in the core because the Gnode API differs a lot from that memory management API that kernels support normally. And at some points there are even deficiencies that you can't solve, so you have to work around it. For instance, capability delegation. On some kernels you have the problem that you have to remember capabilities at certain places where you normally wouldn't have to using the Gnode API, but you have to because the kernel otherwise revokes the capability. So, yeah. Well, we came up with the idea of creating our own kernel. This kernel should trust core because it's trusted anyway, as I said, and should be completely tailored to serve the needs of core. Yeah. And in that, it can be reduced to a minimalistic library that is linked to core and simply enables it to run directly on the hardware. And having the the kernel API, you can also run the most critical parts of the system in in a more simple manner than in core. For instance, core is a multi-threaded application, and and some things are much easier if you are not multi-threaded, for example. So let's talk about a little bit about the kernel itself. The tasks behind the kernel API are at first the exception vectors. Setting up the exception vectors and catching exceptions is a main task of the kernel. Then doing the scheduling, of course, for the multi-threaded components on top. Then the kernel controls the interrupts, of course, because it has the exception vectors. And it provides communication. In our case, it's only two communication channels. You have IPC and you have signals for synchronous and asynchronous communication. Then it supports capabilities. So you have trusted capabilities on top, and you have local names in each protection domain that can't be misused. It does cache and TLB maintenance because on most architectures these are privileged operations. And last but not least, it does virtualization for the same reason as for cache and TLB maintenance. And because it has the exception vectors. The API that rises from these tasks is pretty simple. You can see in the top row, these are all syscalls that are core only. So only the core component of Gnode is allowed to do these syscalls at all. And in the bottom row, you see the public API of the kernel. So these syscalls can be done by each user. And you see these are not many syscalls. It's 14 if I counted right. And it's mostly about threads, signals, messaging, and some capability syscalls to manage the capabilities in the local PD. And all the memory management you can see is the memory management for the kernel. The new and delete syscalls are all in the core only section. So this brings me to the first quality of the kernel, that all dynamic memory is accounted. Because for each kernel object that is created on runtime, you have to put in some memory from the outside, so from core. And in core we have a good memory management, and so this memory management reflects the costs for the kernel objects to the session quota on top of the Gnode API. So in general, for each kernel object you create, you have to pay as user. And this brings with it that the kernel can't run out of memory. And yeah, that's a big advantage of this kernel. And the other thing is that this way the whole kernel is a mere state machine. So you can keep it single-threaded. You don't have any dynamic stuff that is created, and this makes the kernel pretty small. It's really low complex, and all you do in the kernel, every time you're in the kernel, you are the only one that is in the kernel. So you are really fast. You don't block. You are not interrupted, and kernel passes get really fast in general. So, speaking about low complex, I have a little picture here. Normally, if you on Gnode and you have one of the third-party kernels. You have in the basic setup, say, core, the kernel, and the init component, and some bootstrap tools on some kernels. You have at least 30,000 lines of code that you have to trust from every component on top of it. And this is already pretty small, but with this kernel library approach, we can reduce it to about 22,000 lines of code. Yeah. About the hardware support of the kernel. Yeah, initially, the kernel was developed on ARM7, and so the most features it provides on this architecture, of course, it provides several boards. You can see it here, like Freescale boards or Exynos and the OMAP4, for example. And you have various features that are supported, like the ARM Trust Zone features, multiprocessing, virtualization, or FPU, or something like that. And of course, we also support other architectures. Here are some of them, like x86, 64-bit, the ARM6 support we have for Raspberry Pi. And recently we ported the kernel to RISC-V. Done by Sebastian Sumpf. And we also have a board for the Muon separation kernel, which is a project from Switzerland. Yeah. Let's go into more detail. First, I'd like to talk about the scheduling in this kernel. With scheduling, normally on other kernels, on other kernels, we have only absolute priorities for scheduling, and the big problem that you have with absolute priorities is, of course, that if one of your components goes mad at some point, the other components that have a lower priority are not executed anymore. So this is a problem we faced, and we thought about how to solve this in our custom kernel. And we thought that having only the priority, like a quality value, is not enough. We have to have another value that is like a quantity value for CPU resources. And we came up with the quota, CPU quota. CPU quota is like a time slice. You have a super period of 100%. Currently, it is set to 1 second in our kernel, but you can configure it, of course. And of this 1 second, now you can donate parts of it, you can donate slices of it to the several components. And then there's the principle that a component has only a priority if it also has quota. So if you're out of quota, you in principle have no priority, and you get only scheduled round robin. And as long as there is a component that has a priority and quota, it is scheduled before the other components. So, okay, let's look at our example from before. We have again our USB that goes mad at some point, and you can see that in this super period it exceeds its own quota by going mad, and then it's scheduled out, and that's it. And then in these red slices, you can see the scheduler goes to round robin because there is no component left that has quota in this super period. So at the end of the super period, all the quota gets reset. And there are again priorities. And then you start again with the USB because it has gone mad, and then it exceeds its quota again, and it's scheduled away. So this is a nice way of keeping the system alive, even if you have a high priority, but going mad. Yeah. Okay. Another nice thing about the CPU resources is that they can be distributed in a way that resources are normally distributed in Gnode. So you have the parent of a component tree that has a specific amount of quota, of CPU quota. And to fill its children with life, it can give them some of its quota. And these children can again, like CLI gives VirtualBox again a little bit of its quota, and so on and so on. Yeah? So it's in the hands of the parents how much quota their children get. And the same is with the priorities. You have at the root of the tree the init has all priorities, 1 to 8, and then can give a sub-range of these priorities to its children, and so on and so on. Okay. Let's talk about the capabilities a little bit. It's one cool thing about capabilities on the base HW kernel is that the capabilities get automatically created and translated. So normally, when normally you get capabilities into your protection domain by receiving IPC, and in this IPC message are some local names of the other component that sent me this IPC, but I cannot use these local names of the other components. So the kernel goes ahead and tries to translate these local names of the other protection domain to my own protection domain. So I can directly use them without looking up any object or something like that. And so when I receive the message, the local names that I have in this IPC message are already fine for me. I can directly invoke them. And it also, if the kernel now realizes, oh, there's a local name of the sender of the IPC that is not present there is no counter local name in the other protection domain. So the kernel goes ahead and creates automatically one for me. So yeah, I have no invalid local names when I receive the message. Yeah, and this implicitly this implies that you have no name diversity in your protection domain. So if you have one object in the kernel that you want to reference, you can be sure that you only have one name in your protection domain for this object, because they don't get duplicated. Yeah. Okay. And one cool thing about it is that all costs in the kernel that arises from receiving capabilities gets counted to my own protection domain session quota. So the user, if it wants to receive capabilities to its protection domain, has beforehand give the kernel some quota, say, okay, you can use this quota for my capabilities, and as soon as the kernel has the case that it likes to create some local names for me, it takes some of this quota and creates it from it. And if the quota is not sufficient for creating these local names, the kernel says no and throws an exception and says, here I have some capabilities I want to give you, but I have not enough quota. And then I can go ahead and give him some more quota and receive the capabilities. So this is again in line with the concept I told about at the beginning, that the kernel doesn't give its own memory for users, but it always wants to be paid for actions. Yeah. Last but not least, the cool thing about capabilities is that the kernel helps you with the lifetime management. It looks a little bit complicated, but I will try to explain it. In general, if you're receiving a new capability, the kernel has to create a local name object. Yeah? I talk about this at the last slide, and it has to use my quota for this. And of course, it's in my interest to get rid of this local name object as soon as I don't need it anymore. And how to achieve this? The kernel helps me with this. But there's a problem because there's a transition phase. So when the kernel has created the local object here, it has to send it to me. It moves this capability into my UTC-B, for example. And then I have to receive it from the UTC-B and create a local instance and so on, and start ref counting and the whole lifetime management in the user land. But between these 2 points, I have a phase where the local name object is already created, but it is not known to the user land. So if now one thread in my application receives the capability, and another thread also receives it, and during the time that this other thread demangles the capability from the UTC-B, the first thread starts to delete it, it would be fatal to delete the local name object. Because then I would have capability inside that is not adjusted. And this is why we have a cat egg syscall. So the user land has to acknowledge when it has received the capability. And as long as there's an acknowledgement happening, like in this case here, I have to wait until the egg comes. And then the other kernel does the other thread does it to me. And then the kernel sees, okay, there's no more acknowledgement pending, I can really activate the local name. So the whole lifetime management is pretty easy and safe. Yeah. Okay, talking about communication. This is a short topic. First, about IPC. Cool thing about IPC is on the basic W kernel that it implicitly delegates CPU resources. So, if you imagine you have these 4 components, it's 2 components that use a terminal session. It's a simple session where you can put in characters and these characters go somewhere. And you have a multiplexer for the terminal session and a UART where you can print these characters that you put in the terminal session. So if these 2 terminal clients here above start an RPC to their terminal multiplexer, they give their IPC resources to the terminal multiplexer. So the terminal multiplexer has all its own size and the 2 of the clients to process the RPC, and then it does again an RPC to the UART to process its own RPCs, and it gives away all these slices it has for its own to the UART. So the UART now has a lot of CPU resources to process its RPC, and it's just a lot of parts. Resources go back to their original components. So, yeah, and then about signals, the asynchronous communication channel. Again, the kernel helps here with the lifetime management. And here the problem is a little bit different than for possibilities. The main problem is that you have to manage, and this this userland object is the signal context. It's like the type of signals. If you have different signals, like a timer signal or something like that, for each type of signal you have an object to know if a signal arrives, what type of signal is that. So in general you have again a phase, a sequence where the signal arrived. It's in my UTCB again, and I have to update the signal context. So the userland lifetime management is up to date. But during this time slice, it would be fatal if another thread goes on and likes to destroy the signal context, because then the pointer that I got with the signal would be invalid, and yeah, and this is why the kernel has this kill signal context syscall. And if another thread now comes and wants to delete the signal context, it does this kill syscall. And the kernel now knows, okay, this signal is killed, but it's already, there's also an acknowledgement pending. So I have to wait. But I don't accept any more submits for the signal. So the signal is dead, but it's already there. It's still there. And as soon as the acknowledgement of the receiver arrives, this kill syscall of the main thread gets unblocked, and it can start destroying this signal context without having any fear that there is still a signal in flight. So the main advantage of this is that normally you would have, when you receive a signal, normally you would have to look up the signal context. You would have some data structure where all signal contexts are in, and you do a lookup on it every time you have a signal to ensure that the signal context is still available, that it is still alive. And with this system, you won't have to look up signals anymore. And so signaling in general, I think gets faster. Yeah. Okay. That's it for my point. Maybe you have some questions. Otherwise, I'd like. Yeah.
Yeah, if I wanted to play with this, just to check it out, I never worked with this. What would I do?
Yes, of course. You can see here there's the source code of Gino available on GitHub, and then there you have a tool for creating build deals, build directories. And in this build directory, you would have to set the kernel. There's a kernel variable. The build directories are architecture dependent, so we have an x86 build directory, for example, and then you set the kernel variable to HW. That's the name of the kernel. And then all you build in this build directory automatically gets built for. Yeah, and yeah, maybe I can show it. So I have my repository for Gino here, and now I delete the old x86 build directory. architecture. I have to ensure that it is an architecture that is supported by the base HW kernel, of course. So it says successfully created, and then I go to the directory 76, 64. Good. So, and now I have this buildconf file. Where can I configure my building? And here's the kernel variable. You can set this kernel variable also temporarily. Yeah, if you do the make later, you can also set it only for this one make call, but you can also set it in here. I put it here. HW instead of Nova, and that's it. I start a test like this here, the signal test, and now it starts building all the stuff. And you can see here that it builds the kernel-dependent library for the HW kernel. Yeah? We have some kernel-dependent libraries that are linked against the generic binaries, so the binaries stay independent from the kernel. Oh yeah, I forgot. I can also set I enable multiprocessing, and yeah, here it compiles the kernel and yeah the core. Oh, it takes a little bit of time. There's the kernel library. And now it starts. And that's it. Now I have a simple component running on base HW kernel. You can also start fancier tests, of course, but it would take a little bit longer. So yeah. Okay. I hope this answers your question.
Yeah, this is very nice.
Yes. Okay.
It's not a question, it's a suggestion. You should definitely come up with a better name than base HW.
Yeah, I thought about it a lot of time. I thought about lots of different names, and then there was the point, I think everybody knows it, where all the other guys said, okay, we need a name, and I don't have a name, and then they started, okay, let's come up with hardware for example, and I said, okay, well, take it. It's not the coolest name, but I think it's the kernel is not that yeah. It's not an own standing component. Yeah, you don't have this popularity where the name is that much important. Yeah, it's different for other kernels that are used without any other system. Okay.
Two quick questions about the scheduling and about the memory management.
Yes.
You can go back a slide to the scheduling
yes.
where you explained the super period. I didn't get the red dots. Actually, the red dots mean that they didn't get the time to process. They didn't get the CPU time, right?
Okay.
Okay. Why don't they get the CPU time if the super period is not over and there is time and there is no more priority task?
Yes. Yes. Okay. Okay. This is the super period. Yes. Yeah. Until here, and now you have at the beginning lots of processes that have a priority and a quota, and they use their quota like here. And for example, for a foul play, at this point the quota for a foul play is exceeded. Yeah, it has no more quota left for this super period. Yeah. So
using actually the green as to show that the quota is used, not that the quota is available.
No. Yeah, it's a little bit complicated because at this point you are already in the next super period. Yes. Okay. This shows the quota for the next super period. Yes. But for the last super period, at this point, the quota is exceeded for FO play. Yeah. And at this point, for audio, the quota is exceeded, and so on. So at this point, all components except the timer have no more quota.
If a war process or task comes, but there is still time in the super period, it will receive the super time, right? Let's say the timer doesn't get invoked after the USB doesn't require time. So
yes.
lower priority task, let's say the GCC
yes.
will be.
Of course, you can only consume your quota when you're awake. Yeah. So this is why the timer still has quota left at the end of the super period.
And the question about memory management was that you told that any pending acknowledgement
yes.
would make the kernel wait for the.
Yeah, that's a good question. I said that the kernel would wait, but that's actually not true, because the kernel only sets the thread to wait. So if I do this delete,
exactly. The delete happens in the kernel. It's like it says that the kernel waits for the delete.
Yeah. It's not like that. Actually, it's like it's when you do the delete syscall. And no, it's a bad example, because at this point nobody waits. The delete is like a hint for the kernel only, and it directly returns. But for signals, it's true. For signals, the kill syscall. Yeah, when you say I want to delete the signal context. And the kernel realizes, okay, there's an acknowledgement pending, it blocks the thread. Yeah. So the thread doesn't return from the syscall, and at this point it returns.
Okay.
So,
in the previous case?
But the kernel stays alive.
Okay, and in the previous case, from the kernel perspective, can you go just a slide?
Well, no.
Yeah.
Where was it? Here,
yeah, in this case, you said
yes.
that from the kernel perspective, the delete won't happen until the acknowledgement comes.
Yes.
So from that perspective, it's possible that the user space never sends this acknowledgement. What mechanism the kernel has to capture that?
Yes, it's this delay has no effect. Yeah. The kernel only realizes, okay, somebody wants to delete the cap, but there's there's still a representation of the capability in the component in the protection domain, but it has not resolved it yet. So when it gets the acknowledgement, the kernel says, okay, now the userland has the new local name, and then the delete waits for the next delete to delete the.
Maybe I'm not asking the question right, but what happens if that acknowledgement never comes and local name objects keep creating in the kernel? Is there a way for the kernel to realize?
That's no problem,
wrong?
because this acknowledgement syscall is only a help for the protection domain for the user.
Oh.
Yeah? If the user is not intelligent enough to do the acknowledgement, it's its own problem, because it's its own quota that is used for the local name object.
Okay.
Yeah.
Thanks.
Okay.
So I had another question which was related to management.
Yes.
So if I understand correctly, for instance, the file system is in one process or all processes or several processes. But more generally, if you have a process that needs to communicate with another process, who's allocating memory? You mentioned that everybody is.
You mean in case of the capabilities that
yes.
That you have? Okay, so each protection domain has to pay for its own capabilities. So if yes. I'm a server and I provide a session for clients, and over this session I receive capabilities from the clients, I have to pay a server for this.
Okay.
I am willing to spend some of my quota to fulfill the service I provide for the clients in this case.
Okay.
So I have to spend some quota beforehand, before I say, okay, now I'm ready to receive IPC messages. And if I don't, and I get capabilities and the kernel throws an exception, then I can also still decide whether I want to spend more quota for the client or not. It's in my own it's my
So the server will receive the exception if the client cannot connect?
The server will receive the exception from the kernel if the client sends a message where a capability is in that I don't know yet.
Okay.
And the kernel tries to create a local name for me, a capability for me as server, but it has not enough quota for me. So I have the choice to either spend more quota, say the kernel gives more quota, or I say no, I don't want to.
The client send quota, or does it need first the capability?
No, it has to send a quota first.
But it can send the quota without sending the capability.
The quota must be spent to the kernel. Yeah. I don't know if I understand your question right.
Could you make some analogy with kernel with a hypervisor and a guest for this memory location?
What did you say?
Like server client, kernel,
Yes.
VM guest. Like this analogy
Yeah,
with memory with a quota. Would it be easier to?
It's the same for a hypervisor and just in this point, because
So the quota always comes from the hypervisor for the guest, and if the guest requires something more, because we have to go and the priorities and all that.
yes.
Maybe I can try to clarify.
Maybe Norm can try to clarify because the question is, I think he's a little bit more used to hypervisors.
So each component in the system has a certain budget of quota, and there is a protocol that allows components to trade this quota between components. So if you have a server and a client, and at a point when the client wants to have something, use some service from the server, it opens a connection to the server, and with this connection it spends or it donates a bit of its own quota, a bit of the client's quota. But this is something that goes out of band of this RPC that we are talking here. So this has already happened. So the client has donated some of its own quota to the server, and so the server knows, okay, this particular client has given me this amount of memory, and so that the server can say then to the kernel, okay, now I'm filling the kernel a bit more of my quota. So they are counting the client, but the concept between the kernel and the component, this is the topic that Martin is talking about.
Okay. There are no more pressing questions. I'd like